Hello there, welcome back. In the last video, we discussed the circuit theorem, that is the Thevenin theorem and substitution theorem. And uh, in this video, we'll discuss Norton theorem, which is a dual of the Thevenin theorem. Let's see what Norton theorem has got to say. So basically, uh, just as we used voltage for theorem, we will use current for Norton theorem. And in the same way, we have a, let's say, a big network of linear elements, resistors, voltage sources, and independent sources. And let's say we again have a terminal from two nodes, and the terminal we have again we put up a resistance. We found that the resistance has a potential drop across it Vx, so we replace it by a constant voltage source Vx, and a current Ix flows in this given direction. So this is what the situation is. Now the goal is to simplify the network into as few elements as possible, like we tried in the Thevenin equivalent. So let's see how can this be approached for current. So Ix current was going out of the terminal into the voltage source. So again, this can be understood as a superposition of the network with independent sources and without independent sources, some of those two. So let's say step one, we have all the independent sources. They are not null yet, and in this case we will just short circuit uh, the terminal and measure the current through it. We call it in the Norton current. And in step 2 we will null all the independent sources. That is, the circuit now just comprises of resistors and dependent sources. And we put up, let's say, a voltage source across the terminal, that was Vx, any Vx. Okay. And now there will be a current going through it and some Vx as we have applied. So we can measure the resistance across it. That will come out to be again measuring the I and V parameters at the terminal. We'll get the resistance, that is RTH, just as in the Thevenin case. And at this point what we will see is, since once again, the after removing the independent sources, the network can be realized as just a resistor. We will have a current Vx by RTH flowing in the opposite direction, opposite of In. Because in this second diagram you can see that if this is a resistor, the current will be driven by the voltage source Vx. That, so we'll call it minus Vx by RTH with the negative sign indicating direction. And on superposition we'll find that the Ix of the main circuit we started with can be written as In minus Vn by RTH, considering both the cases, step 1 and step 2. And after that, once we have Ix, this equation can be realized by a simple circuit, that is a constant current source In, a resistor RTH in parallel, and the external voltage source Vx that we had again in parallel. So Vx can be anything, any value that maybe depends on the external components that we use across the terminals. But basically this network has now been reduced just to a current source and a resistor in parallel this time. Since they are a dual of the Thevenin, we have parallel here and a series over there. So this is the Norton equivalent of the system. We can just go we have just simplified what the network was. And again, from a quick understanding point of view, we just need In and RTH once we know what Norton equivalent does. So how to find it quickly? First, In, that is just the short circuit current through the terminal. RTH, the same way as we did for Thevenin, short circuit, null all the independent sources and measure the resistance across the terminal. And that's it, the Norton equivalent. Connect them in parallel, and there you have the entire network. This is how Norton equivalent goes. And one more quick theorem that we can cover here is the maximum power theorem for resistive and, let's say, current voltage sources based circuits. That is, it will get a bit different when we deal with capacitors and inductors later, but as of now it is quite simple. So once we have let's say any network we are dealing with, and across the terminals we want to put a resistor, a load, and we want to draw the maximum power from it. So what will be the, what should be the load resistance so that we can extract maximum power? This is what the max power theorem tries to address. So the entire network can be visualized once again by its Thevenin equivalent, just VTH, RTH, and that's it. What, however big the network be, as long as it is comprised of linear elements, this can be done. And now these are the terminals across which we want to connect a resistor and find the maximum power. So what can we do? So the approach is as follows. Like, let's say connect a resistance of value R. The current flowing through the entire circuit will be VTH by RTH plus R. This current, when flows through R, will give a power, let's say that will be V I square R, that is VTH square upon RTH square, RTH plus R whole square times R. Now R is a variable here in this expression, and VTH and RTH are constants. We want to maximize power, so there are multiple methods. We can directly differentiate, or use tricks like the EMG inequalities or whatever. We get the power to be maximum when the external load resistance R equals RTH. When R equals RTH, we get maximum power, and that maximum power, when we substitute it back into the equation, we'll get it to be VTH square by 4 times RTH. This is also known as the available power of the circuit. And yeah, that's it. That was all about the maximum power theorem. And in the coming video, we'll try to understand a new concept quickly. That will be two-port networks, and quickly summarize what it has got to say. So thank you for watching, and see you there.